Good. All right, we're back. So last time, there it is. I did 19. 20 is actually just, if you interpret what 19 is saying. So I could probably move on from 19. 19 and 20. 21 is probably similar, but maybe it would be good to start there. Question says, it is possible to write an integer in 2 to the n minus 1 ways as a sum of smaller positive integers. If they differ in the order of the terms that's considered different. So like these are three different sums. So for instance, 4, you'd get 2 to the 3 minus 1, which is 8 minus 1. There's 7 different ways to express 4. We happen to have counted these up on a previous question, but yeah, I don't know that one off the top of my head. Never mind this little scribble. We're looking at 21, and it says there's this many ways to express a positive integer n as a sum of lesser terms. So you're ignoring the one case of just n. But you are allowed to have the terms. You're allowing 1, 2, up to n minus 1. Smaller positive integers. Yep, that's what it says. Well, we could probably have reviewed these previous applications, but let's see if I can just remember it. This is analogous to, there was one question he asked where it was like, if you only use the terms 1, 2, 3, and 4, and you wanted to sum up, like you want to sum to say 10, for instance, but the different orders will give you a different sum. So like pretend these are stamps and you're putting them on an envelope, and the order matters. So like 2, 4, 4 is different than 4, 2, 4, etc. And they wanted to know how many sums are possible. That's the same question as this, except that they're allowing more of these. The way he had done this previously, pretty sure you want to start with 1 and then do like zeta square, etc. That represents 0 ones or 1 1 or 2 1s, etc. up to as many as you want. We could even stop at n, since we're not going higher than that if you really wanted to make it a finite thing, but it's easier this way because then you can just express it as a it's written out as a power series. You can just write it as a geometric series. And then we'll have zeta squared, and then basically just powers of zeta squared. So again, it's a geometric series. And then you do this again with 3 and with 4. And for some reason I kept screwing up the, I was doing like 3 squared is 9, I'd write a 9 here, but yeah, you want to get all multiples of, in the exponents you want all multiples of those numbers. So here it's like 8 and 12, etc. So you get a product here like zeta cubed, and then again a geometric series with zeta to the 4. That's this example. So in our example up here, we're just going to do the same thing, but with n minus 1. So this would continue. You'd have this, oops, I mean plus, times, you'd keep going, until you stop at zeta to the n minus 1. Now if you think back to, I was checking our result in 919. Unfortunately, that's just odds down here. So even though it looks awfully familiar, it doesn't apply directly. Anyway, I could probably continue my thought process here. If you were to expand this mess, the coefficients represent the number of solutions. So we would be trying to show that this is what you get as the coefficient for this expansion. I think this was actually what he called Bn. If we look back at like number 9, he reviewed all of them. Or maybe it was just he skipped B. Oh, no, here it is. Postage stamp problem, call it Bn. Did I somehow get this wrong? Yeah, I did. Huh, wonder what I was doing. Oh, yeah, see, like, I guess what I just did was more like the change problem. This was like part AN. So yeah, this is wrong. That's good news, because it wasn't making any sense to me. But yeah, when I combine these, when you multiply these, it removes the ordering. This is basically just combinations. So like 4 and 2 gives you 6. And the only other way you get 6 is like this guy times the 1, right? So it's clear that the order doesn't matter. It's like this times that is the same as this times that. You only consider that once. But we're trying to make that, we're trying to include an ordering. So this was wrong, my thought process there. What I meant to do is, I remember the answer because I just looked at it, but it comes from the postage stamp one, which I guess was this Bn. I'll call it, I don't know, distinct sums. But it comes from powers of this zeta, zeta squared, zeta cubed, zeta to the 4. If you raise this to a power, then you get S terms. Does that make sense? S terms of this form, 1, 2, 3, or 4. So we're doing the same thing. We're going to sum over various powers, zeta to the 1, zeta squared, up to n minus 1. So take that to the k and let k go from, we're not going to have one term, so we'll start at k equal 1. Well, I should probably really even just start at k equals 2, but I was going to skip k equals 0 case because you're not going to get the number 1. But like if you sum this up along with 1, then you get this as a nice form for it. Yada yada, like that. So now the concern is, how do you get this as a coefficient when you expand this? Back to square one. Well, I guess one thing that occurs to me, we're looking for Bn, and I do remember there was a formula like, when we did it with 4 terms, you get Bn is the sum of the previous 4. So the same formula would be like this. You'd add all of these up, going all the way down to 1. Could involve some sort of multinomial theorem, right? It's a little gory. I mean, you could expand this, and you should have just a formula right there for the BNs. Yeah, I'm not seeing it. So I guess we're going to cheat and look at 21. That's quite the answer. So, of course, it's the coefficient of this series. He then... Sure, he rewrites this sequence as that and sort of solves it like this. That's fine. And then he factors it out, writes out powers of 2 zeta. Oh, wow. And then he also has another argument here. It just has to do with lengths. This is more of like a, I don't know if I want to call it geometric, but if you just look at a subset, just look at an interval. Wait a minute, was it supposed to be a single? I don't think it's a single term. Maybe I misread it. No, it's not a single term. That second argument was really slick. He was just saying you'll have n minus 1 options, and you either choose it or you don't. So it's like a super fast probabilistic type of, or discrete math type of approach. I wasn't gonna stumble across this trick, but that's clever. That's that I could do. I can understand that. He's saying take this form of it and then write it like this is zeta over 1 minus zeta, and then simplify this. So you get 1 minus zeta, well, minus zeta. So it's 1 over 1 minus 2 zeta over 1 minus zeta, right, like that. So you're getting this. And then he factored it. And then this is just a geometric series, like 1 plus 2 zeta plus 4 zeta square, etc. And then so if you took this and subtracted zeta times it, you'd end up with Okay, so take this and just subtract zeta. It's kind of weird. Oh, no, it's not. It's not. It's reducing the next entry by 1. That's where you're getting the minus 1 from. So you get like, if there's a nicer way to write that. So you get a 1 out front, of course. And then you get, instead of, well, here, it's 2 to the 1 minus 1 zeta. And then 2 squared minus 1 in front of zeta squared. And then 8 minus 1, etc. And that explains, you know, in general, this is like our B3. This explains in general that Bn is 2 to the n minus 1. So I'm okay with that. That I would follow with no issue. His other argument was, if you have an interval of length n, there's these integers inside, like marked 1, 2, up through n minus 1. But the sum of this thing, that is clever. Like it could be n of these lengths, or you could think of it as a length 2 plus a length n minus 2, or, you know, all sorts of combinations. Yeah, this is really simple. I basically just need like the sum of the segments. He's now associating each segment length with one of the terms that's less than n. So I would think you're counting segments, not integers. He seems to immediately say, okay, well, you have n minus 1 options, and you either use it or you don't. And that's how you get 2 to the n minus 1. Okay, for each integer inside this set, you have these lengths, these line segments that are length 1, 2, 3, etc., up to n minus 1. You either use that segment or you don't, and that's where you get this number. That doesn't make a whole lot of sense to me, although we are counting all the possible ways. Yeah, I must be missing something a little bit. Alright, back to it. It says the integral is a sum of subintervals of integral lengths. And you choose, where you choose some of these points as the points of division. For each of them, there's two possibilities. You would choose it or not. Really is that simple. For some reason I'm not. So for instance, like 2 is either used or it's not. I guess it's... okay. So I guess if you thought about, like, in terms of the multiplication principle, or whatever, this counting principle, you choose the first term, you have n minus 1. I don't love that. I was going to say you have n minus 1 options. the second one, or the after, the ones after that, you don't. It's not like you just suddenly get n minus 2. So this is the wrong way to think about it. It's like a big set of cases. Yeah, the logic is good, I just don't. You have these numbers 1 through n minus 1. He's just saying, yeah, you either use it or you don't. Until you get 2 to that power. Huh. Okay, so if you're going to use my logic here, you have n minus 1 slots, and at each moment you make a decision. That's why I'm so confused, because like you can't just. I can't just pick 2. I can't just be like, yeah, this is on, this is off, this is on, this is off, because it's not going to sum to be n. Oh, wait, well, yeah. He didn't say you use it once. He said you use it, period. It's either involved or it's not. So it could be multiple terms. Like you could have multiple ones. Also, this is a weird way to think about it because we're not actually constructing. No, that's not a horrible way to think about it. Every time I come up with like a binary number of length n, so for instance for 4, this could represent whether we used, which numbers we used. So already you're seeing I'm like confused because this number I wrote down represents both 1 plus 3 and 3 plus 1. But in any case, his logic was like we either use it or we don't. So you have 2 in each one of these slots, and we're going to remove 1 just because we're excluding that one case where. So on this last one, you could put a 1 there if you want. We're not allowed to choose 4. So this will lead you to 8 options using the numbers 1, 2, and 3. And then, of course, we subtract 1 for some reason. We subtract, I guess, the one case. If you had just let all these options be like no, 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 and then yes, we subtract 1 because we're removing the 4 case. Yeah, I've definitely done this before. I'll have to think about this again. I don't know why I'm having such a hard time with it. If you just read it again. interval is a sum of subintervals of interval length, where some of the n minus 1 points are chosen as points of division. Oh, okay. It's not quite the way I was thinking about it. These literal points, like these endpoints of segments, you either use it or you don't. Like, say you use every single one of them, then you're getting 1 plus 1 plus 1. But if you only use a couple, like you use this one is on, this one's off, this one's on, then you get 2 plus 2 plus, n minus 4. That's what he's counting. So for these, yeah, okay. It's hard to abstract that. Sorry to like write it down practically outside of this image. You're just drawing n minus 1 slots, 1 for each point, and you're saying you're either chosen or not, and you get 2 to the power of n minus 1. And then the one we remove is if they were all, like, if you don't choose any points on the inside, then the only point you get is this. We want to remove that one case. Okay. I guess I don't need to think about it again. That makes sense. So I wrote this, but it's really like the line segments. Well, no, that's the point. It's not the line segment. It's actually like, do you use this point or not? It's the endpoints that you're looking at, and you're choosing to include that as part of the division. The division is the sum. As part of your partition of this interval, you could have used these points or not. All right, yeah, that's kind of a clever way to count it. Anyway, that's 21. Let's get back to the battle. 22 says total number of integral solutions to this set of Diophantine equations is n plus 1. So the right hand side is decreasing. In general, you're getting this. Well, at the end, you're getting this. Yeah, these two. So there's like n plus 1 equations here. If I sort of add opposites, not that we're going to do that, but if you add like this to that, you'll get equals n on the right hand side every single time, and you'll have n plus 2 with n plus 4. But that's kind of a silly observation. So I'm looking at 22, of course. It's x plus 2y equals n, 2x plus 3y equals n minus 1, etc. Down to nx plus n plus 1 y equals 1, and n plus 1 x's, n plus 2 y's, sum to be 0. Find number of solutions to this system, integral solutions. Well, along with 0. I'm sure this is going to be something silly. So this is the same as the making change problem. If if we just looked at this one, you know, if we just had n equal 1, that's pennies and, I don't know, two pennies. um, Anyway, what I'm saying is this top one, the way you would have approached just that one is to, you know, here's the 1 case, you get 0 ones, or 1 1, or 2 ones, all the way up. For the 2s, you get none of them, or 1 of them, or 2 of them, etc. So you end up with a product like 1 over 1 minus zeta times 1 over 1 minus zeta squared. And we're looking for the coefficient in front of the nth term of that expansion. For this next, well, so what's annoying about this is that the right hand side is not going to be n every time. Like this is going to change the right hand side, and also we're looking for n minus 1, not the nth coefficient anymore. And this last one doesn't only have the one solution. It's just x and y equals 0. And let's see, yeah, it doesn't have any other solution. So this one's a 1. I mean, it really depends on what n is now. But if you had an example like n equals 1, you'd be solving this system for n equals 1 case, and I guess you would only have 2 solutions. If you had a bigger situation, right? Again, you always get one solution here. This time you have 2 up here. And in the middle, we have none. No solutions on that one. That's interesting. So you get 3. I mean, I guess I could keep going, but that's not going to really... I don't think that's going to shed a whole lot of light on it. So the n equal 3 case, it's like that. Again, this is one solution, this is none. This is one solution, and this has like at least 2, right? 2. So we're getting 4 solutions there. Don't love it. So another way to think about it is you're summing up like, what is this, I said it was the change case. Yeah, it's the change example. It's like the first series example he gave us. So in a sense you're summing up, well, I can't just call it, but it's something like an plus prime an minus 1 plus double prime an minus 2. These primes represent different series. So instead of 1 and 2, it's like 2 and 3 or 3 and 4. And of course it always ends on 1. Is there ever going to be a way to even make this one? No, right? We kept getting 0 because even the only time we didn't was when n was 0, or 1. I don't see how this is ever going to have a solution, that one. I mean, it doesn't. It's a non-negative integral solutions for x and y. I think am I thinking about this wrong? No, these are separate. Yeah, they want like collectively the number of solutions, total number of solutions. It's not like we're doing a system where they're all true at the same time. It's Yeah, I'm a little stuck on this one. I'm sure it's going to be something. So we're looking at 22. Yeah, first of all, this is what I just said. Wait, why is there no 0 on this option? Oh, because he scaled it. Good. He like, in order to make them match up, remember how I was complaining that I'm looking for the n minus first coefficient. So that's how he corrected for that, is he threw a zeta in there and made it the nth coefficient, and then he throws a zeta squared in that one and makes it, he like forces it to become the nth coefficient again. So I'm with you here. I agree with this first part. That's basically what I got. Then something clever happens. He was doing what? So if you add these fractions in here that are being subtracted, if you actually subtract those out, you'll get this minus that. You'll get the first, zeta to the v plus 1 minus zeta to the v plus 2. the next step. Because he's saying, like, it's almost like he knew the answer ahead of time and went backwards. I'm sending it zeta to the v plus 1 minus zeta to the v plus 2 over the 2, you know. He was looking at this. So of course you can factor E out, you'll get zeta minus zeta squared. That's where that comes from. So this is somehow the same series that we were looking at up there, the product of them. If you factor this part out, it'll cancel with the junk that he had written there. You know, on the bottom he had the same term. Oh, there it is. Okay. Yeah. This is what we had. So it is the same. He just introduced this thing so he could make it telescoping. He introduced this factor into the numerator so that you could split it into a difference like this. Right? But in order to do that, he needed to put he needed to divide by this factor that he introduced. So v here can go from 0 on, I suppose. Alright, well, what's your point? Once you've got this telescoping thing. Yeah, we could actually solve it. So at 0 you get one term, and then if you go off to infinity, I mean the rest of them cancel. Sure, the limit is 1. So the answer is n plus 1, evidently. Oh, okay, yeah, I see. I was just kind of spacing out here, like how, what? This one is just zeta squared, zeta cubed, etc. If you divide by that, you get back to a regular series, like a regular series in zeta, a geometric series. Yep, you do. And then there's an extra factor. Well, it's that squared. That's what's a little bit confusing to me. Isn't this just like, isn't this just 1 over 1 minus zeta squared? Oh yeah, that's true. That's what that would be. If you just look at like the Taylor series for that geometric function, like 1 over 1 minus x. Is there another easier way to say that? I mean, I'm seeing that this is 1 over 1 minus zeta squared. No, maybe not. Probably not an easier way to see it, no. Yeah, why would you get an n? That's like a confusing... Yeah, that's pretty confusing, unless you were already familiar with the Taylor series. So, what I'm saying now is, if you had... guy's derivative is, you know, the negative of, oh, no it's not. It's actually positive still, because of the chain rule. But anyway, its derivative is this, and this is what I had wanted a series for. But I have a series for this. This one is just that. So when you differentiate it term by term, you'll get kx of k minus 1. The first one goes away, so if you want, you could just plug in a 1 here. Of course, I'm missing, oh, you want to shift. That's why. Okay, so now if you want to start at 0, you can, but you'll be getting this series. Okay, and that's where that came from. So this I never would have thought of. This, you know, this telescoping sum representation of all the products. He basically did this. He said, I followed the beginning because I started to get that as well. We get this, like the nth coefficient of this series is what we want. And then to that, here we want the n minus first coefficient, right? Which is confusing and annoying, so instead just multiply it by zeta, and it changes your series, yes, but it shifts them all. So now you want the nth coefficient again, and you just keep doing that, yada yada, so it's zeta to the, say, v, and then down here we'll have v plus 1 and v plus 2. Yada yada, onward until we sort of stop at n plus 1 and n plus 2 for this. I guess maybe you can't see it anymore, this top equation. Mind those. And so yeah, how would I have continued from there? I know now that, like, it's this, right? Yeah. In general, it's the sum of these as v goes from 0 to n. Okay, it's the sum of zeta to the v over yada yada as v goes from 0 to n. Although we don't have to stop at n. You just keep going because we're looking for the nth coefficient. So you can go off forever if you want. Anyway, we want the nth coefficient of the sum. Yeah, that's right. So why would I think... okay. He kind of made it match up. I guess that's just if you were used to telescoping series. He then took this and multiplied by this. Multiplied and divided by it, of course. Because now he's getting v plus 1 minus v plus 2, which, yeah, I can see it now. Fair enough. So if you had zeta v plus 1 minus zeta v plus 2, and it was over stuff like 1 minus zeta v plus 1 and 1 minus zeta v plus 2, you can sort of see that that's, you know, the numerator could have been this. 1 minus zeta v plus 2 minus 1 minus zeta v plus 1. And there you go. Now you're able to cancel. Anyway, yada yada, sum, yada yada, sum. Interesting. Well, we'll call that 22. 23 says tunnel number. I think we're going to come back to these because there's two more. Actually, maybe close to three more that are almost the same. This one's odd, right-hand side, but otherwise it's the same structure. Total number of solutions of these equations is less than n plus 2, and the difference is equal to the number of divisors of n plus 2. Well, we're going to look at this next time. But for today, we got through 22, I suppose. Thanks for popping in. Have yourselves a great day. I looked at, we're still in section 1, part 1. Today I looked at, last time I did 1920. So I kind of skipped them. In fact, 20 looks complicated, but it's literally just 19. So today we only did 21, 22. But yeah, that's sort of plenty for one day. Anyway, I'll hop back on hopefully tomorrow, maybe the next day. Arrivederci, people. Have a fantastic day.